so looking at this problem, we've got log base 4 of x plus 3 plus log base 4 of 2 equals log base 4 of x squared plus 4. So when I'm running through my strategies, deciding which one I want to use, I know that it's going to be 1 or 2 because I've got logs involved. And then I just have to decide, am I going to use strategy 1 or strategy 2? Now, strategy 1 says that we convert between logarithmic and exponential form, while strategy 2 is the fact that if we have a single log on both sides, we can set what's in the logs equal. Now here, I don't have a single log on both sides, but everything has a log, right? All 3 terms have a log. So that means I can take this side right here and condense them to get it to a single log on each side. So remember, addition condenses to multiplication. So log base 4 of x plus 3 plus log base 4 of 2 is going to become log base 4 of x plus 3 times 2 equals log base 4 of x squared plus x. Okay, now that I have that, I have a single log on both sides of the equations, I can set what's inside the logs equal. So I'm going to just rewrite it like this for ease, but we can take x plus 3 times 2 and set it equal to x squared plus x. Okay, this is very clearly a quadratic, so first thing I'll do is I'll distribute that 2 to get 2x plus 6. Then I want to get everything on the other side of the equation, right? So I'm going to subtract 2x from both sides, subtract 6 from both sides, and that'll give me 0 equals x squared minus x minus 6. It's a quadratic, so we factor it x minus 3, because we want that to be a negative x, and x plus 2, right? Leading coefficient of 1 means that we're just looking for what multiplies to negative 6 and adds to negative 1. Okay, then we're not really done yet, right? We've got to set our factors equal to 0, and we'll get x equals 3 and x equals negative 2. Okay, but those are not automatically our answers. We have to check them. Now, x equals negative 2 isn't automatically off the list just because it's negative. Remember, when we're checking these to see if they work or not, we're checking to see if they give us a negative inside of the log. So I'm going to go back to my original equation, right? You always look at your original equation when you do this. And I'm going to go ahead and plug in 3. So we'd get log base 4 of 6. That works. That's not a negative, right? We're just doing a domain check. Remember, the domain of a log, the domain on a log is 0 to infinity. So we're just checking to see is what's inside of the log in that domain. So then when we do it to this term, right, we can skip this term because 2 works. 2 always works. We'll have, 9 plus 3, which checks out. It's positive. Okay, now when we look at x equals negative 2, well, log base 4 of negative 2 plus 3, that's going to be log of 1, and then negative 2 squared minus 2 is 2, right? We'll have 4 minus 2, which is 2. Well, both of those check out, right? Both of those end up working. Even though x equals negative 2 is a negative number, when we plug it in, it doesn't make the log negative, so it works. Both answers are correct. So if we look at this problem, 4 to the x minus 4 equals 17 to the 3x. We know that we are in the strategy 3 and 4 territory, right? Unlike the other two, this is an exponential, right? So it's going to be one of those two. We start off by just seeing if we could use strategy 3. Can we make these bases match so that we can use the exponential property of equality? That's probably one of the easiest methods. So if we can use it, we want to. But when I take a look at 4, oops, that is a highlighter. When I take a look at 4 and 17, well, 4, I can rewrite that as 2 squared. 17, it's prime. The only thing I can rewrite it as is 17 to the first. So unfortunately, strategy 3 is not going to work, so we have to take to strategy 4. Strategy 4 allows us to use the power property of logarithms to bring down the exponent. So rather than solving an exponential equation, we're now solving a linear or quadratic equation. So what I'm going to do is, given what I have, I've got 4 to the x minus 4 equals 17 to the 3x. I'm going to take the natural log of both sides. Okay, I want to make it clear. You could also take, if we did log of 4 to the x minus 4 equals log of 17 to the 3x, that would also be perfectly fine. We could also do that. But I like to use natural log because I'm lazy. It's 2 letters. The thing you can't do is you can't use like log base 4, log base 5, 17, any of that, because that's not something that we, with the calculators that are accessible to us, had you been taking this in person, can use. So we want to get our answer in a way where if I wanted an estimate for what x is, I could type it into my calculator and figure it out. So you got to use log or natural log. And then the point here, the reason we did this is because now we can use the power property of logs and our exponents come down front, right? So we'll have 4, x minus 4 times natural log of 4 equals 3x natural log of 17. And believe it or not, this is a linear equation. It looks really complicated. It looks like it's something that, we're not maybe familiar with. But it honestly is solved in the exact same way as if I had, something like, just like this, right? I would distribute, get the x's on the same side, isolate x. We're going to do the same thing here. We just have to be a little more careful because it looks weird. We've got that natural log there. So I'm going to start by distributing natural log in. So we'll have x natural log of 4, minus 4 natural log of 4 equals 3x natural log of 17. Now, remember, this is how you write it. It's 4 times natural log of 4. Natural log of 4 is a number. It's not 4. This does not equal natural log of 16. No, you cannot multiply a number into a log. Natural log of 4 is its own number. So now that we have that, we're going to go ahead and get the x's on the same side. So I'm going to subtract x natural log of 4 from both sides. Okay, over here it cancels and we're left with negative 4 natural log of 4. On this side, we're in a little bit of a problem here because we can't just, like, those aren't like terms. It's not 3x minus x. It's not 17 minus 4. 3 times natural log of 17 is an irrational number, and natural log of 4 is an irrational number. So because we can't actually combine them, we can't subtract them, we're just going to leave it as such, okay, which can seem problematic. It can seem like a problem because how on earth are we supposed to solve for x now, right? We have 2 terms with x. Well, that's kind of exactly the point, right? When you have 2 terms that have something in common, you can pull that thing out. So I'm going to factor out an x from both of these terms. That will leave me with 3 natural log of 17 minus natural log of 4 on this side, and then over here I still have, negative 4 natural log of 4. Okay? Next thing we would want to do is actually our last step. We're already there because I've got x that I'm trying to get by itself. Well, the only thing happening to x right now is it's being multiplied by this massive thing. So I undo it by dividing by said massive number thing. Cancels over here. I do it to this side. 3 natural log of 17 minus natural log of 4. Well, now all I've got left over here is x, which is, what I wanted. And on the other side, I'll have negative 4 natural log of 4, 3 natural log of 17 minus natural log of 4. Okay, now I know nobody's like, oh yeah, I know exactly what that number is, right? I have the perfect estimate for that. I know what that means. No, so that is again why we decided to use natural log or log, because if I needed, for whatever reason, if this was an actual equation that came from a realistic phenomenon, this answer, while it's correct, it doesn't do much for me, right? I don't, if I'm trying to measure something and you tell me that it's that many inches long, that doesn't help. So we could type this into our calculator and get an answer, which is why we use natural log or log. Okay? All right, let's take a look at this one next. We've got log base 4 of x plus 2 equals log base 4 of 4x minus 9. So again, we're in the boat where we've got logs involved, so we know that we're going to use strategy 1 or 2. But in this case, we have a 2 on the left-hand side with a log, and then a log on the right-hand side. So neither of our strategies can be used right out the gate yet. We can't convert to exponential form right now, and we also don't have each term with a log, so we can't just drop the logs, right? We can't set what's in the logs equal because 2, it's not a log. So what we actually need to do is what we always do first, condense. I can't condense anything because my logs are on the same side, or are on different sides. But what I can do here now is if I subtract log base 4 of x from both sides, right? I can do that. It's a positive term, so I'm going to undo it by subtracting it. I'll be left with 2 equals log base 4 of 4x minus 9 minus log base 4 of x. Okay, now I can do my condensing. Subtraction condenses to division. So this becomes log base 4 of 4x minus 9 over x. Okay, then I can use our property, the fact that y equals log base b of x is the same as b to the y equals x, where I keep my bases the same, so base 4, and then my input and my output switch. So we'll have 4 squared equals 4x minus 9 over x. Okay, 4 squared is 16, so we'll go ahead and replace that with 16. And now we can actually solve out this problem, right? What we're going to do, we can't solve it when we've got a fraction here, is we're just going to multiply both sides by x to undo the x on this side. We'll have 16x equals 4x minus 9. Okay, subtract 4x from both sides. We'll have 12x equals negative 9. Divide both sides by 12, and we get that x equals negative 3/4. Okay, it can be tempting when you see just one answer to be like, yeah, I've got one answer. I don't need to check them. It's got to work. But we always have to check our answers. We can't just leave something hanging like that. So let's go ahead and check, right? Remember, you always check in the original, the unmanipulated equation. So we'll have log base 4 of negative 3/4 and log base 4 of negative 3/4 times 4 minus 9. Okay, and here's the problem. Neither of those work, right? Remember, the domain of a log is 0 to infinity. Neither of those inputs fall between it. So there's actually no solution to this problem. When we plugged it in and checked it in the original, we got no solution, right? We got a negative inside the log, so this problem is now done. It doesn't have an answer. So here you could probably guess, we've done 3 problems, we've used strategies 1, 2, and 4, that this is going to be strategy 3. But there are some telltale signs as to why this is strategy 3, right? The first one is it's got to be 3 or 4. We're working with exponentials here, so my only option is 3 or 4. But then when I look at 8 and 4, even if I don't right off the bat know how to rewrite them, there's something about them that looks similar, looks familiar. It should be encouraging me to try and find a way where I can write them the same. And what I'm going to do is just rewrite them in the ways that I can. So I guess this would be a little different if, say, we had like something like 16, right? Because 16 can be rewritten as 2 to the 5th. Just kidding, 2 to the 4th. Or it can be rewritten as 4 squared. So, sometimes there's numbers with multiple rewritings. In this case, 8 and 4, while they can't be rewritten with either base, like, I can't rewrite 4 with a base of 8 or 8 with a base of 4. 8 is a perfect cube. 4 is a perfect square. So I can rewrite 8 as 2 cubed, and I can rewrite 4 as 2 squared. Okay, remember, I'm not doing anything to the equation, because remember, if I wanted to square both sides or square one side, I would have to square both sides. Whatever I do algebraically to one side, I have to do to the other side. So we're not doing any algebra here. We are simply making an educated choice to rewrite these numbers. 2 cubed is 8. I haven't changed this equation one bit. Because now, if you look, when we have exponents stacked like this, we multiply them. So we'll have 2 to the 3 times x minus 1 equals 2 to the 2 times x squared minus 1. And now that we have the same base, we can take the exponents using the exponential property of equality, and we can set them equal to each other. So 3x minus 3 equals 2x squared minus 2. Okay, alarm bells should go off saying, hey, this is a quadratic. I need, to do what I got to do. I'm going to get everything on this side because I like having a positive leading coefficient. You do what you want so long as you can factor it. So we've got 2x squared minus 3x plus 1. Now, for me, this one's pretty easy to kind of factor in my head. You can use whatever method you want, so long as you have justification for your choice. And my justification that I would write here is, well, 2x squared is only possibly x and 2x, right? That's the only thing that can multiply to 2x squared. 1 can only multiply to 1 and 1. They multiply to a positive, but add to a negative. To multiply to a positive, but add to a negative, both need to be negative. So for me, that was the quickest way to factor it. But again, if you can factor, that's all I really care about. So long as you can factor, we're good. So 2x minus 1 equals 0. X minus 1 equals 0. This will give us 2x equals 1. X equals 1/2. X equals 1. Now, I should have done a better job talking about this on the first exponential problem. But for exponents, remember an exponential function, the domain is negative infinity to infinity. There's no restrictions on what you can plug in. Because the domain of an exponential function is negative infinity to infinity, I can plug anything in. I don't need to take the time to check my answers. I could, because again, it's algebra. You can check your algebra, but I don't need to. So we're going to call both of these our answer, because they are.